Hi there. In this lesson, we're going to cover section 4.2 in the textbook, which is all about the strengths of acids and bases. So we've got 4 goals in this section. The first 2 are related. The first thing that we're going to do is we're going to contrast strong and weak acids and bases, and we're going to compare that to concentrated versus dilute acids and bases. So they're kind of related but different. We use them the same in English language, but in chemistry they mean different things. The last 2 goals is that we're going to use a table to compare the relative strengths of acids and bases. And then we're going to write acid and base ionization constant expressions for weak acids and bases as well. So the first thing that we have here is a picture to kind of differentiate between what a strong acid and a weak acid or base is. On the left-hand side, you can see a strong acid. On the right-hand side, you can see a weak acid. And if you take a look at the picture, what you can really see the difference is the number of bonds that are made. With a strong acid or base, those ionize 100%, so they split up 100%. So for example, a strong acid releases 100% of the hydrogen ions that it creates. In a weak acid, you'll notice that there's a lot here that are still unbound. There's actually an equilibrium between bound and dissociated molecules here. So that's the difference between a strong and a weak acid. It doesn't have to do with if it can burn you or hurt you or harm you or anything. You can have a strong acid that's very dilute. You can take a hydrochloric acid and make a solution that's 1 × 10⁻⁶ moles per liter. That's a strong acid still, but it's very dilute, so it's not likely to harm you. On the other hand, you could have a weak acid, but have it very, very concentrated, so it could still burn you. So there's the difference between strong and weak, and concentrated and dilute in our solutions. So moving on to the next slide, if I can get it to advance. Technical difficulties here. Is that my Ka is going to equal the concentration of hydronium times the conjugate base of that acid times the acid, just like we did up at the beginning there. One other thing that you'll notice is that the more hydronium ions that we get, the stronger the acid is going to be, because our equilibrium is going to lie more to the right. We're making more of those ions. If we've got a higher concentration of hydronium ions with the stronger acid, that's going to make my Ka go up. So if I have a high Ka value, that one is a stronger acid. Now it's a stronger weak acid because it still doesn't dissociate 100%. Ones down here, whoops. The ones down in the middle of the table here are all of my weak acids. So hydronium ion, iodic, oxalic acid, for example, all of those are my weak acids. The bases are not named, but they're still on the right-hand side of the table. So those are all weak bases. They all have associated Ka values. And you'll notice that they're really weak. They're stronger at the top, as indicated because they've got a larger Ka, and the acids get weaker and weaker and weaker as you move down the table. And you can see that with the Ka values. They get smaller and smaller and smaller. With the conjugate bases, it goes the other way around. And we'll look at how to calculate Kb next week. But as the acid gets stronger, the base gets weaker. So they're inversely related. So there's just a few summary notes to go through what I just talked about. So coming back to this, the other thing that you'll notice is that even though OH- and NH3 are listed on the left-hand side of the table, they do not act as acids, just in the same way that the conjugate bases of these strong acids never get to act as a base. So they do not give up hydrogen ions in water because that's a one-way reaction, because it's a strong acid or a strong base. Okay, the other things that you should note about this table is that the Ka values listed are for aqueous solutions at room temperature. So just like any equilibrium constant, they are temperature dependent. So we can't go and change the temperature and expect that our Ka or Kb is going to stay the same. We'll learn to calculate the Kb's as we go along. One other thing that you might have noticed if you were paying attention to this chart really well is that some are found on both sides of the table. So here's an example. We've got HSO3 minus. It's also found down here as an acid. So it's found as an acid and as a base. And if you think back to our last lesson where we had water acting as both an acid and a base, this one is amphiprotic. So these are amphiprotic and are able to act as either an acid or a base. So hydrogen sulfide ion is one example. Bicarbonate ion, HCO3 minus, is another one. You can find it on both sides as well. So you can kind of do a little scavenger hunt and see which ones are amphiprotic. What this means is that for that particular equation, the products are favored. So there's the first example. Here's another question. We've got predict whether the reactants or products will be favored when HCN, hydrocyanic acid, reacts with the hydrogen carbonate ion. So with this one, I have a little bit tricky here. I have to figure out which one gets to act as the acid, and I have to predict my products. Now with this one, it is a little bit trickier because both of these can act like an acid. However, only one of them can act as a base. So if we look on the right-hand side of the table, you'll find that HCO3, the hydrogen carbonate, can act as a base, but HCN can only act as an acid. That makes this hydrocyanic acid the acid in this case. So when we predict our products here, the acid is going to lose that hydrogen ion. We'll get Cn minus, and the hydrogen carbonate ion is going to accept the hydrogen ion. It's going to lose its charge, and it's going to become carbonic acid. So on the right-hand side, I've got an acid and a base. Now I'm going to go and I'm going to compare my two acids. I'm going to look at the chart and see which one is stronger. So here we can see that the carbonic acid is higher on the chart than the cyanic acid. So that means that this reverse reaction is going to take place more than the forward reaction, and that means that my reactants are going to be favored. Now in this next scenario, we've got a case of amphiprotic. So we're actually going to have to compare a few things on the chart. It says, predict whether the reactants or products will be favored when the hydrogen sulfate ion reacts with HC2O4. Okay, so we've got hydrogen oxalate ion and hydrogen sulfate ion. So I'm going to begin by writing this out, and then we're going to determine which one is the acid and which one is the base for that forward reaction. So for this one, I don't have a case where only one can act as an acid. Both of them can act as an acid, both can act as a base. So before I even get started with figuring out whether the products or the reactants are favored, I actually have to figure out what my full reaction is going to be. So here I'm going to identify hydrogen sulfate ion, and I am going to identify the hydrogen oxalate ion on that chart. You can see that this hydrogen sulfate ion is stronger. So it's going to act as the acid in this case. And this one's going to act as the base. So that acid is going to donate the hydrogen ion. The base is going to accept it. So I've got oxalic acid on the right-hand side, and I've got that sulfate ion as my base. Now I have to go back to the chart and compare again. I'm going to compare between the two acids. So I've got oxalic acid up here and the hydrogen sulfate ion again on my chart. You can see that the oxalic acid is the stronger one. So that oxalic acid is going to act as the acid and shift that reaction to the left-hand side. That forward reaction is not going to happen as much, and so in this case, the reactants are going to be favored. And there's a lot of questions for you to try this week that will hopefully get you through some of these questions. So for these, we've got some practice problems. It says for the following, complete the equilibrium and predict whether the reactants or products are going to be favored. With this one, I've got hydrogen peroxide, H2O2, and the hydrogen sulfite ion, HSO3-. We can predict our products here. The peroxide, hydrogen peroxide, only acts as an acid. So we know that it's going to go to HO2- after it's donated that proton. And we're going to have H2SO3. With this one, we're going to compare the two acids. You can see that sulfurous acid is stronger than peroxide, so the reactants are going to be favored. Next one, we've got citric acid and ammonia. So I've got H3C6H5O7 plus NH3. And with this one, again, we've got one that can only act as an acid, one that can only act as a base. So I'm going to have H2C6H5O7- and NH4+. I'm going to compare the two acids. So I've got this one here and this one there. And in this particular one, the H3C6H5O7 is the stronger one. It's going to push it to the right-hand side, and my products are going to be favored. Next, I've got the hydrogen carbonate ion, HCO3- plus H2PO4-. We've got that in equilibrium. So with this particular one, because they're both amphiprotic, I had to go through and I had to figure out which one of hydrogen carbonate and dihydrogen phosphate was stronger. With this one, the hydrogen phosphate is a stronger acid, so it gets to donate the hydrogen ion, turns into HPO4. Now I'm comparing the carbonic acid and the dihydrogen phosphate ion. And what I'm going to find is that that carbonic acid is stronger, pushing equilibrium that way, and the reactants are favored. So I really encourage you to go through those examples, try and find all of those things on your data table, and make sure that you know what's going on. Okay, second to last question here, we have arsenic acid reacting with an equal concentration of sulfate ion. And at equilibrium, we're told that the H3ASO4 is in greater concentration than the hydrogen sulfate ion. Write the equation for this reaction and state which acid is the stronger one. So with this one, if you go to the chart, you'll find that not everything is found on the chart. So with this one, we're going to actually have to do a little bit of detective work, figure out what's going on to have these results. So the first thing that I'm going to do is when I write out that reaction, I have to identify which one's going to act as the acid and which one's going to act as the base. I know that my sulfate ion cannot donate any hydrogen ion, so it has to act as the base. So with my products, I've got H2ASO4 minus plus HSO4. And we're losing one from its charge, so it just has a -1. So now I have this acid and base on the product side. Now it tells us that at equilibrium, the concentration of H3ASO4 is greater than the concentration of HSO4-. So we're comparing these two acids right now, and we're told that there's more of these ones. What that means is that equilibrium must lie with the reactants. Lies on the reactant side. So that's kind of pushing that equilibrium and favoring the reactants in this particular one. The only way we get the reactants favored is if the product side has the stronger acid. So what we can conclude here is that the HSO4 minus is the stronger acid. And this sort of detective work was really important for setting up that chart in the first place in order. So that's one of the reasons why we might want to do something like this. Okay, last question in this problem set is we're going to consider the reaction between the sulfite ion, so we're going to take SO3, 2 minus, and hexaaquochromium ion. I know this is the first time you've seen hexaaquochromium ion. The formula, you can look it up on your data table. We've got 6 waters that are bound to a chromium, has a positive 3 charge. Even though it looks scary, it behaves like all the others. So don't let that throw you off. And we're going to predict whether the KEQ is greater than or less than 1. So first thing that I'm going to do, I'm going to identify my base and my acid. The sulfite ion cannot donate, so it has to accept the hydrogen ion. So one of those waters in the hexoaquochromium is going to be broken down. And you can see that we've got an acid and a base on the product side. Now, we want to predict whether KEQ is greater than or less than 1, which is basically another way of saying are the products or the reactants favored. So we're going to compare the two acids. I've got an acid here and an acid here. You'll notice that the hexoaquochromium ion is stronger than the hydrogen sulfate ion. So that's pushing equilibrium towards the product side. So we're favoring the products. And we know that KEQ is equal to the concentration of products over the concentration of reactants. So we know that if we're favoring the products, that's going to increase that numerator and decrease the reactants, and it's going to move my KEQ to something greater than 1. So we can conclude here that KEQ is greater than 1. So I hope that helped you out going through those notes. Please try the worksheet. That worksheet is really, really good for working you through how everything kind of goes together and getting you into the more difficult problems. So please don't skip it, and good luck. Let me know if you have any questions.